Okay, so this is the video lecture for section 4.1. So in particular, chapter 4 is on exponential and logarithmic functions. So exponential and logarithmic functions. And in particular, 4.1, we'll start talking about exponential functions. Okay, so I'm going to start off by motivating this with an example. Let's say we have two situations, right? So we have two towns that are experiencing population growth. And let's say town A starts with 1,000 people. And its population increases by 100 per year. Okay, so they initially start with 1,000 people, and their population increases by 100 people per year. And in town B, starts with 1,000 people, so same initial conditions. And its population increases by 10% of its total number of people each year. So its population increases by 10% of its total number of people each year. Okay, so what I want to do is I'm going to create a little table that gives the population for town A and town B for each year, like year 0, year 1, 2, 3, 4, and so on. Okay, so let's create that table. So there's going to be 3 columns. So the first column will just be the year. And then second column will be the population of town A. And then the population of town B will be the last column. Okay, so if the year is 0, right, that's easy, then the population of town A is 1,000, and the population of town B is also 1,000. If the year is 1, then the population of town A must be 1,000 plus 100, right? Because it increases by 100 each year, and that's going to be 1,100. For town B, it'll be 1,000 plus 10%. So how do I do 10% of 1,000? 0.10 times, remember, of means multiplication, of 1,000. And if you work that out, well, 10% of 1,000 is 100, so this is also 1,100. Okay, year 2, the population of town A will be the previous year's population, so 1,100, plus another 100 individuals, right? So that would be 1,200. For town B, it'll be the population of the previous year, so 1,100, but then plus 10% of 1100. And that turns out to be a little bit more than 1200, around 1210 in this case. And in the third year, town A would be the previous year, 1200, right, that population, plus an additional 100. So that would be 1300. And town B would be the previous year, so 1210, plus 10% of the previous year. And that turns out to be 1331. Let me do one more. And in the fourth year, town A would be 1300, right, plus 100. So that would be 1400. And in town B, it would be 1331 plus 10% of 1331. And that equals 1464. And so on, right? And we could continue this process. Just dot, dot, dot. And keep going. And you notice that town B's population is going to be growing more quickly than town A, and eventually, once we get to much larger years, it'll be much more quickly. Okay, so it turns out that town A's population we can model as linear growth. So we can model it with a linear equation. So let me show you that. So town A we can model growth, meaning population growth, as a linear function. In fact, if you think about it, right, if I call the population P, the total population P, so it's going to be a function, right, of the time in years. I'll call the time in years T. Well, that's just equal to 1,000, the initial value, plus, and it's going to be 100 times T, right? It's just a linear equation. If T is 1, then it's 1,000 plus 100 times 1. If T is 2, it's 1,000 plus 100 times 2, and so on. So town A is exhibiting linear growth. Town B is very different, right? And I want to do this carefully, look at town B's growth carefully. So for town B, here, I'm going to do another table here. Let's say this is the year. And then this is the population of town B. Okay, so year 0, right, very straightforward. It's a starting value, just 1,000. Year 1, the population of town B was 1,000, right, plus, remember, 10% of 1,000. But another way you could write that is you could factor out the 1,000, right? It's common to both terms. You could bring that out front, and you're left with 1 plus 0.01. Okay, and that equaled 1,100, right, ultimately. But I'm going to leave it like that, as 1,000 times 1 plus 0.10. Then year 2, we have 1,100 plus 10% of 1,100. But I could factor out the 1,100, right? I could pull it out front. So I have 1,100 times 1 plus 0.10. But remember, 1,100 itself is just, so the 1,100 here I can replace by up above, it's just 1,000 times 1 plus 0.10. And I'm still multiplying by another 1 plus 0.10. So I could write this as 1,000 times 1 plus 0.10 squared. Okay, and in the third year, are you guys following this this sequence. So in the third year, I have that amount, and actually this is equal to the 1210, right? This is equal to 1210. So the third year, I have 1210 plus 0.10 times 1210. But again, you could argue, oh, I'll factor out the 1210, and I'm left with 1210 times 1 plus 0.10. But the 1210 itself is equal to 1,000 times 1 plus 0.10 squared, and I'm multiplying by another 1 plus 0.10. So this is going to be 1,000 times 1 plus 0.1 cubed. And so on. And you can guess, right, that if we keep going, so year 4, you could probably guess this by looking at the pattern here. Year 4 is going to be 1,000 times 1 plus 0.10 to the 4th. And in the 5th year, it'll be 1,000 times 1 plus 0.10 to the 5th, and so on. And actually, we can keep doing that until we get to, I'll call it the t year, right, where t is any integer, 0, 1, 2, 3, 4, 5, and so on. So what is that going to be? Well, that'll be 1,000 times 1 plus 0.10 to the t. So what we can say is that the population for town B, I'll call that P again, as a function of t, is equal to 1,000 times 1 plus 0.10 to the t. And this represents exponential growth. When the variable, in this case the t, is in the exponent, right, it's going to be an exponential function. So this represents exponential growth. Right, and the difference is, see how in this case the t is in the exponent, right? Our independent variable, our input is the exponent. Whereas in the linear case, we're just multiplying times t, right? The equation was 1,000 plus 100 times t. Here we're raising it to the t power. So at first it doesn't look like there's much of a difference in the population, but then as t gets larger and larger and larger, this grows very, very fast. This population will grow very quickly. Okay, so let me formalize what an exponential function is. Give you like a formal definition of it. Okay, so exponential function So an exponential growth or decay function that grows or shrinks at a constant % growth rate, is a function that grows or shrinks at a constant % growth rate. So is a function that grows or shrinks at a constant % growth rate. The equation, so an exponential function, can be written in the following form. I'll just say it can be written in the following form. There's actually a couple of different ways you could write it. You could write it as f of x is equal to, so I'm using x now as my independent variable, is equal to a times 1 plus r to the x. Or you could also write it this way, as f of x is equal to a times b to the x. And if you do that, we're assuming that b is equal to 1 plus r. Okay. Either way, there'll be some cases where we use the first form, some cases where we use the second form. Okay. Now, what are these parameters a, r, and b? So let me define those here. So a is just the initial. Let me do it this way. So a is the initial value of the function. Right? It's a starting value. It's the value when x is equal to 0. So when the input, right, is equal to 0, when you do f of 0, you're going to get back just a by itself. So it's the initial value of the function. R is the percent growth or decay rate. And it's going to be written as a decimal. And it could be positive or negative. Actually, if R is positive, it represents growth. If it's negative, it represents decay. So let me write that somewhere. So I'll say positive means growth. Negative means decay. And then finally, B, you can think of as the growth factor. So we're going to define it as the growth factor. And remember, we know that B is equal to 1 plus R. And we're always going to assume that B is always positive. So I'll say we will assume B is positive. Otherwise, it jumps back and forth. It doesn't make much sense to have B negative. So for this class, we're going to assume B is positive. Okay, so here's an example. Let's say, I'll do an example where we have like a decay. Let's say you're told a population of 1,000, so 1,000 people, is decreasing %3 each year. Find the population in 30 years. Okay, so let's give variable names first. So first of all, we'll let t equal the time in years. right? R is our growth or decay rate. In this case, it's decaying by 3%. So remember, decaying means R is going to be negative. And if we want to write it as a decimal, so what's 3% as a decimal? It's 0.03, right? You have to move that decimal point 2 places to the left, or you can think of it as you're dividing by 100, right? 3 divided by 100 is the same as moving the decimal point 2 places to the left. So R in this case is going to be negative 0.03. And then what is the starting value? Well, the starting value is our A, and that's going to be 1,000, right? We start at 1,000. Okay, so the equation for this then is going to be the following, right? The function is going to have this form. It'll be the population at some time t is equal to A times 1 plus R to the t. So if I want to figure out the population at 30, I can just substitute in 30, okay? But first, actually, let's put in these parameters. So I have, for my specific case, I have P of t, the population at time t, is equal to A is 1,000, then 1 plus negative 0.03 to the t. And if you want, you could write this as, I could write it in the other form. So this is kind of like the A times 1 plus R to the t form. But I could combine the 1 and a negative 0.03, and I could write this as P of t equals 1,000. And then this would be 0.97 to the t. So now it has that like A times B to the t form, right? Either one, they're really equivalent. You're just combining the 1 plus R to get B. Okay, so how do I answer my question? Simply plug in 30 for time. Remember, t is the time in years. So I want the population when t is 30. So that'll be 1,000 times 0.97 raised to the 30th power. So you have to do this on your calculator. And you should get 401 people. Right, the units are people. So it's decaying, right? It's decreasing over time. Okay, next question. I want to find a formula for an exponential function passing through 2 particular points. All right, so let's see if I can squeeze this in the bottom here. So find a formula for an exponential function passing through let's say the point 3, 1 and 5, 4. Next section we'll really start looking at these graphs, but for now I just want to come up with an exponential function where those 2 points satisfy the exponential function, right? Because it's passing through those 2 points. The graph passes through those 2 points. All right, so the way to do this type of problem is, in general, we start with our general exponential function, which we're going to write as A times B to the x. Okay, so now, if you want, you can call f of x something else. You can maybe call it y. So y equals A times B to the x. And these 2 points are x and y, right? X and y, the input and the output. Again, you can call the y f of x or y, it doesn't matter. So if I plug in those 2 points, then I'm going to have the following, right? I'm going to have, in the first equation, if I plug in 3, 1, so where I have a y, I plug in 1. Where I have an x, I plug in 3. In the second equation, where I have a y, I plug in 4. And where I have an x, I plug in 5. Okay, now there's a couple of ways you could solve this. So now we have 2 equations, two unknowns, right? But they're not linear equations. In fact, they're very nonlinear in this case. But we could still use the idea of substitution. Another way to do this is just to divide the equations. Here, so I want to solve for A and solve for B. That's the goal here. So how about this? What if I write this as, all right, AB to the fifth equals 4. And I want to divide that by the second equation. AB to the third is equal to 1. Why is this helpful? Because look what happens to the A's when I divide, right? I'm dividing both sides. Divide the left-hand side, divide the right-hand side. So if I divide the left-hand side, A's are gone, right? A over A is 1, so those are gone. B to the fifth divided by B to the third. Remember, when you're dividing powers and they have the same base, the rule is you keep the base and you subtract the exponents. So 5 minus 3 is 2. And then 4 divided by 1 is 4. And then how do I find B now? Well, I need to take the square root of both sides. And really, right, it should be plus or minus. So B is going to be plus 2 or minus 2. But remember, we said that B, we're always going to assume it's positive. So the one that we want is the B equals plus 2, right? We don't have to worry about the negative 2. Okay, great. So we have B, right? We have our answer for B. Now we just have to find A. Well, how do I find A? I go back and I plug into one of those equations. So maybe I'll go back and plug into this first equation, right? So I have 1 is equal to A times, I know B is 2 now, right? 2 cubed. So 1 is equal to 8 times A. And if I divide by 8, I get A is equal to 1/8. And now I'm done, right? I have my equation. So the actual function is going to be f of x is equal to A, which is 1/8. And then times B, I'll write this way, to the x. So that's the equation of the exponential function that passes through, where the graph passes through 3, 1, and 5, 4. So in other words, 3, 1, and 5, 4, those 2 points will satisfy that equation. By the way, if I write this in the other form, let me go to the next page. Actually, here, I'll go over to the right here. So I have f of x is equal to 1/8 times 2 to the x, right? And so I have it written in this form. F of x equals a b to the x. What if I write this in the other form? F of x equals a times 1 plus r to the x. They should be equivalent, right? Well, if b is 2, then what is r going to be? R has got to be 1, right? Because b is 1 plus r. So just subtract 1 from both sides. If you have, so b2 is equal to 1 plus r. So if I subtract 1, r is equal to 1. So what is the percent growth rate if r is 1? Remember, that's a decimal. How do I convert that back to a percent? Now I multiply by 100 or move the decimal 2 places to the right. So what this is saying, that in this example, I have 100% growth rate. Okay, but the key thing here was assume it had this form, f of x equals a times b to the x, and then we had to plug in the two values for x and y, the 2 points that we had, and then we were able to solve. We had 2 equations with 2 unknowns. We were able to solve for a and b. And once we have a and b, we're done, right? We have our exponential function. Okay, here's another example. Okay, so here's an example from the textbook. It says that a house was valued at $110,000 in the year 1985. The value appreciated to $145,000 by the year 2005. what was the annual growth rate between 1985 and 2005? Assume that the house value continues to grow by the same percentage, right? So it's undergoing exponential growth. And we also want to know, what did the value equal in the year 2010? Okay, so we need to find, right, the general exponential growth function. So what I'm going to do is I'm going to give some variable names. I'm going to say like maybe V is equal to the value of the house. And maybe T is the time in years since 1985. Time in years since 1985. So what does that mean? Well, let's think about that for a second, right? If the year is 19, keep making mistakes today. If the year is 1985, that means the time, right, T, if T is the year since 1985, is going to be 0. If the year is 1986, that means T is going to be 1, and so on. Right? So actually, if you want to know what T is for a particular year, just take the year and subtract 1985, and that'll give you T. Okay, so we know two things, right? We know that when T is 0, so initially, I'll call this like T1, right? When it's 0, what is the value of the house? Well, it's got to be 110,000. 110,000. So we have that initial point, right? When T is 0, V is 110,000. When T is 20, and why am I using 20? Because I know another piece of information. I know by the year 2005, and if you do 2005 minus 1985, that'll give you the 20, that the value of the house is 145,000. So I'm going to call this like T2, V2. Okay, so the general equation, right, this is going to be an exponential function, right, because it's growing by the same percent each year, right? So it's got to be modeled by an exponential function. So since V is the value of the house in dollars, T is the time in years since 1985, I can write that general function the following way. I can write it as V of T is equal to A times 1 plus R to the T. Or if I want, I can call 1 plus R B. That's probably the best way to do it. Just use a B for now. And if we want to figure out R later, we can easily get R, right? Once we know B. Okay, so let's plug in these two particular points into that function so we can solve for A and B, right? The whole goal is to figure out A and B, and then we'll have our answer, and then we can answer any other question from that. So if I plug in the first point, when the value is 110,000, that's when T is 0, right? Initially, 0 time, the value is 110,000. Okay, this is nice because what is B to the 0? What's anything raised to the 0 power? It's 1, right, by definition. So that tells us that A is 110,000. We kind of knew that, right, because A should be the starting value anyways. And now for the other equation, What else do I know? I know that when the value is 145,000, we already know A, so I can plug that in. This is 110,000. And this is going to be B to the T. But what's the time when the value is 145,000? It's when T is equal to 20. Okay, so I need to solve that equation for B. How do I solve this equation for B? Well, first of all, you want to isolate the B to the 20th. So let me write this again. I'll write it so the B is on the left-hand side. So to isolate the B to the 20th, I want to just divide by 110,000 to start. So I'm going to get B to the 20th is equal to, this is around 1.31818. Okay, now how do I get B by itself? Well, if I have B raised to the 20th and I want to undo that, I need to take the 20th root, right, of both sides. So I'd literally have to do the 20th root of B to the 20th. That'll give me B, but whatever I do to one side, I have to do on the other side. So I have to take the 20th root of 1.31818. Okay, so how do you actually do this in your calculator? So again, left-hand side, that gives me the B. That's what I wanted. Right-hand side, the way you do this in your calculator is you raise this. So use your caret. And then how do you represent the 20th root? Remember, you can write it as a fraction. It's 1 over 20. So the exponent is 1 over 20. And that'll give you the correct value, which in this case, if you work this out, if you do this on a calculator, you're going to get 1.014. Okay, so that means that the actual function now for the value of the house, v as a function of t, is going to be 110,000 times 1.014 to the t. Or if you want to write it the other way, as 1 plus r, this is going to be 1 plus 0.014 to the t. Right? Because remember, we know that b is equal to 1 plus r. So if I want to find r, that's got to be b minus 1. So r in this case is going to be 1.014 minus 1, but that's just equal to 0.014. Right? This is the same as that. But actually, this tells us what that growth rate is, right? If we wanted to know r, it's saying that r is 1.4%. That's the growth rate. Okay, now I had one more question I needed to answer, right? I wanted to find the value of the house, assuming it still undergoes this same exponential function. What is the value of the house in the year 2010? So to figure out t, I need to do 2010 minus 1985, right? And that gave me 25. And then I just need to plug it in, right? So I want the value evaluated at 25. So this would be 110,000. I'll just use the first form, 1.014 to the 25th. Again, you have to do this on your calculator. And you should find that you're going to get $155,719. So that'd be the value of the house in the year 2010, assuming it still undergoes the same growth rate. All right, great. Okay, so now the other really important application of exponential functions is compound interest. So I want to talk a little bit about compound interest next. So compound interest, and what that means is you calculate the interest multiple times or many times a year. That's what I mean by compound. So it's calculated many times per year. So let me give you the general formula to start with, and you'll see that it's really an exponential function. So compound interest can be calculated using this formula. So A at t is equal to A times 1 plus R over K, and then raised to the K times T. Okay, so what do all these variables stand for? Well, first of all, the left-hand side, A of t, this is like my output, right? This is the amount in the account at t years. So I'll say is the account value at t years. Think of it as amount, right? A is amount. T is the time in years. A is the starting value, just like before. It's often called the principal in this case. So A is the starting value of the account, but that has a common name that everyone uses. It's called the principal. R is the annual percentage rate. So it's the annual growth rate. People often call this the APR. So when you hear APR, that's what they mean, the annual percentage rate. And then K is the number of compounding periods per year. So for instance, like if an account is compounded quarterly, then K would be 4, right? It's compounded 4 times per year. If it's compounded monthly, K would be 12, and so on. Okay, so here's an example. Let's say this is our question. So if 4% is invested in a bank account at an interest rate of 7% per year, find the amount in the bank after 9 years if interest is compounded annually, quarterly, monthly, and we'll skip continuously for now. I'll come back to that later. So annually, quarterly, and monthly. All right. So we know the basic formula, right? In fact, we just wrote it down. Let me write it down again. I have the fact that A of t is equal to A times 1 plus R over K to the KT. So let's do annually first. So annually, what is K going to be if something's compounded annually? annually, k is just equal to 1, right? It's the number of times it's compounded per year. So if it's annually, it's just equal to 1. So that means the formula is now going to be this. It's going to be a, and we want to know how much money we have after 9 years. So t is equal to 9, right? And little a is the starting value, or our principal, that's $4,000. And r in this case, since it's at an interest rate of 7%, then our r is going to be plus 0.07. Okay, so I have a of 9 is equal to 4,000 times 1 plus 0.07 over 1, and then it's going to be 1 times 9. So if you work this out, right, this is going to be 4,000. This turns out to be around 1.07. Actually, it's exactly 1.07 in this case, to the 9th power. And then if you plug it into your calculator, you're going to get $7,353.84. So if it's compounded annually, that's how much money you'd have in 9 years. If you started off with $4,000, the interest rate is 7% per year, and it's compounded annually. Okay, what about quarterly now? So let me bring up a new page. So quarterly, well, what does that mean? It means k is equal to 4, right? But everything else is the same. R is still going to be 0.07. A will still be 4,000. T will still be 9, right? Everything else is the same. So now I want A at 9 again, but now k is 4. So this will be 4,000 times 1 plus 0.07 divided by 4. But then I have to raise this to 4 times 9. Right? So if you work this out, this is 4,000. This is like 1.0175. And then 4 times 9 is 36. And that turns out to be $7,469.63. So you get a little bit more money, right? If it's compounded more often, more than once per year. If I go to monthly now, again, what's the change? Everything is the same except k now. Well, if it's compounded monthly, how many times a year is that? K's got to be 12, right? So now I have the amount after 9 years is 4,000 times 1 plus 0.07 divided by 12 to the 12 times 9. So this is equal to 4,000. Then I kind of rounded this, 583. And then 12 times 9 is 108. In this case, you're going to get 7,494.03. So we even get a little bit more money, right? There is a limit to this. It's when you compound it continuously, but we haven't talked about this yet. So I want to do that next. Like, what does it mean to compound something continuously, right? Which means like every nanosecond you compound the interest. In fact, it's even more than every nanosecond, but that's sort of the description many, 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 many times, right? It's continuously compounding. Okay. One thing you should see from here, though, is that if you compound more than once per year, the actual interest in a year is more than the annual percentage rate, right? Actually, let's talk a little bit about that before I go on to continuous compounding. So let me write that down here. So if you compound more than once a year. The actual interest in a year is more than the annual percentage rate. So actually one way to explain that is the following. Okay, so let me do another example. Let me explain this a little more carefully. So let's say we want to compare when $100, so I'll say compare these values when $100 is invested at 10% for 1 year. So here, I want to make a little table here. So the first column will be the frequency of compounding. And then the second column is going to be the value after 1 year. So I'm investing $100, right? 10% is my APR, my annual percentage rate. And I want to find the value after 1 year, depending on how many times I compound the interest. Okay, so if it's compounded annually, then that's going to be equal to the interest is going to be based on the APR, right? Because if you plug into the formula annually, it's going to be A, which is 100, times 1 plus R, which is 0.10, divided by 1, because remember K is 1 in this case, right, if it's annually. And it's raised to the K times T, but T is just 1 in this instance, right, because we're only doing it for 1 year, so T is equal to 1 in this case. And if you did that out, that of course is going to be $110. Right, so that's based strictly on the APR itself, right? You make $10 interest. Okay, what if I do this so that annually I compound it semi-annually? Well, what does that mean? That means that K is equal to 2, right? So now this formula becomes 100 times 1 plus 0.10 over 2 raised to the 2 times 1. We're still doing it for 1 year. And this is going to give you a little bit more money, right? In fact, it'll be $110.25. Okay, what if I do it quarterly? So I compound it quarterly. So now K is equal to 4, right? K is the number of times per year that you compound the interest. So this will be 1 plus 0.10 divided by 4 to the 4 times 1. And that turns out to be $110.38. And you can see you get a little bit more money, right? Not a lot, but a little bit more. If I were to compound it monthly, then what is K? It's 12, right? So this would be 0.10 divided by 12 raised to the 12 times 1. And that, again, is going to be a little bit more. It'll be $110.47. And then we'll do one more. Let's say you compound it daily. Well, we're going to round a little bit, right? We're going to say there's 365 days in a year. So this is 0.10 divided by 365 raised to 365 times 1. And that turns out to be, again, a little bit more, around $110.52. So if you compound it more frequently, right, more than once per year, the actual interest is going to be greater than what you get just from the annual percentage rate. Now, one way of seeing this is we could calculate the percent increase. So let's actually calculate the actual percentage, right, the percent increase for daily compounding. So the actual for daily compounding. And to do this, I'm just going to do like, just like it, as if you're solving like a percent increase or percent decrease problem, right? So if you want to find the percent increase, well, I started at $100 and I ended up after 1 year having $110.52, right, for daily compounding. So what's my percent increase? Well, it's going to be the final amount, so 110.52, minus the initial, which was 100, divided by the initial. And then times 100 just makes it a percent, right? You multiply by 100 to make it a percent. So if you do this, you're going to find that you're going to get 10.52%. Right? And remember, and so what I'm saying is that this percentage is greater than 10%, which was the APR. Right? So if you compound more than once per year, you're going to have a percentage that's actually greater than your APR. Right? Percent increase that's greater. Actually, this has a name. This is called the annual percentage yield. So this, the 10.52% in this case, this is called the annual percentage yield, and the acronym for that is APY. So what it's saying is if you compound more than once per year, you could think of it as you're getting an APR of 10.52%, right? As if it's as if you compounded it once per year at 10.52%. Does that make sense? So if you compound, 365 times a year at 10%, that's the same as compounding once a year at 10.52%. So that's what they mean by the annual percentage yield. And actually, we can compute the annual percentage yield for any amount and any number of compounding periods. Actually, let's derive the formula for that right now. So in general, we can compute the APY for any amount and any number of compounding periods. Well, how do we do that? Well, I know that the amount I'm going to have after 1 year, right, if I compound, k times per year, that's going to equal, in general, to A times 1 plus whatever R is, right, over K, whatever the number of times I compound per year, to the K times 1, because I'm just doing this for 1 year. So how do I find my percent increase? Well, my original amount was A, right? So my final amount is this amount. So I'll leave it in general as A times 1 plus R over K to the K. I subtract my original amount and I divide by the original amount. So what you can do is, to simplify this, is you could factor out an A in the numerator. So I'm going to be left with, I'll write it like this, with 1 plus R over K to the K minus 1 over A. Do you guys see that? So, right, if I distribute this back in, I'll get what I started with. So I'm factoring out, I'm taking out the A. And notice here that I can cancel these A's. So actually, that's the equation for the APY. It's simply going to be if you want to calculate the annual percentage yield, it's going to be 1 plus R over K to the K minus 1. Okay, and it'll give it to you in a decimal form, right? If you want to write it as a percentage, just multiply by 100. Okay, now I want to talk about the limit. Like, what happens if you keep going? You compound annually, then semi-annually, then quarterly, then monthly, then daily, hourly, once a minute, once a second, once a millisecond, once a nanosecond, and you keep going until you get to continuously. So what happens if we try to do this? Well, we're going to find that this is going to lead to a very important number. In fact, it happens to be an irrational number named E. So this is what brings up it's sort of like the natural base of an exponential growth function. Very, very important. So let me describe this. So there is an upper limit to the amount when increasing the number of compounding periods. You're going to find that E is like one of the most important functions. E to the x is one of the most important functions that you deal with in calculus, for those of you going on to calculus. So actually, let me say that this leads to a very important irrational number named E. Okay, so here's the example that we're going to end up deriving E from. And we're going to do it using compounding. Okay, so let's say that we have $1. So we start with $1. And it's invested at 100%. So our R is equal to 1, right? This is saying our R is equal to 1. So 100% interest. And we'll do this for 1 year. So we start with $1. It's invested at 100% interest. So R is 1 for 1 year. So I'm going to make another table here. So I have frequency. So how often it's being compounded, and then the value at 1 year. Okay, so we'll start with annual. Right, so if it's compounded annually, then remember the formula is the original amount A times 1 plus R, but R is also 1 in this case, raised this divided by K, which is 1, raised to the K times 1, because T is 1. So this is going to be equal to 2, right, if you worked it out. So it'd actually be $2 in this case. If you don't want to think about, here, I'll leave it in terms of money. So do $2. Semi-annually. So what's the difference? The only thing that changes is K now is 2. And if you work that out, it's going to be $2.25. Okay, quarterly. So now K is 4. So this is going to be $2.44, another little bit, like a tenth of a cent there. So that's the amount of money you'd have if you compounded quarterly. Monthly. So K is 12. And that turns out to be $2.613. And of course we can keep going. So daily, I won't keep writing down the entire equation, but it's going to be a little bit more, right? It'll be 2.715. K is 12 in that case, right? Hourly, K is 365, it's daily, right? And in hourly, K is now what? K is going to be 365 times 24, right? Some really large number now. And if I work this out, if I plug it all in, I'm going to get $2.7181. If you do once a minute, so now K is some huge value, right? It'll be 365 times 24 times 60, right? Because there's 60 minutes an hour, whatever. So some really, really large number. You work this out, and you're going to find it's $2.71827. If you do once a second, it'll be 2.71828. And it turns out, you can see this is sort of like reaching some limit, right? Where it's not getting any larger. And it turns out if you're to do this continuously, then you end up with a number that's 2.71828. And of course I'm rounding because I have to. So this number goes on forever, right? It never ends. It never repeats. It's an irrational number. And this is E. Well, in this case, it's approximately e if I stop. But if I wrote the whole thing out, right, to infinity, that would be exactly equal to e. So it reaches a limit. And that limit is that number e. So another way of saying this, right? Remember the formula for compounding was, we had $1. I won't even write the 1 out front. But we had $1 out front. Then we had 1 plus 1 over k raised to the k times 1, right? So I'll leave that one off as well. Well, what happens continuously, what that means is I take the limit as k goes to what? It's getting larger and larger and larger and larger, right? K was 1 for annually, 2 for semi-annually, 12 for monthly, 365 for daily, 365 times 24 for hourly, and so on. It's getting larger and larger and larger. So what happens as k goes to infinity? Well, this value, 1 plus 1 over k to the k, as k goes to infinity, is equal to e. So as k gets really, really, really big, that expression there goes to e. It goes to that number 2.718282, and so on. Very important. Certainly not obvious, right? But very important. So given that, let's derive now what they call the continuous compounding formula. So continuous compounding formula. Okay, so I'm going to start with this. I'm going to start with my usual compounding formula. So A at t is equal to A times 1 plus r over k to the kt. But I'm going to make a substitution here. I'm going to let m equal k over r, right? Or another way of saying that is k is equal to m times r, right? I can multiply both sides by r. All right, why am I doing this? You're going to see in a minute why this helps us out, because we're going to get the 1 plus 1 over k to the k comes out nicely when we do it this way. One thing you should notice here, remember r is a constant, right? So as k goes to infinity, and we're assuming r is some positive annual percentage rate, right? So it's some positive value. So as k goes to infinity, if r is just some constant and you multiply it by m, what's happening to m? M is also going to infinity, right? If I have, infinity times 0.01, that's still infinity. So as k gets larger and larger and larger, that means m is getting larger and larger and larger. Okay, we'll need that later. So let me do this substitution now. So where I have k, I'm going to plug in m times r. So this is going to be mr, I still have a t there, right? Okay, now what happens to the r's? Well, the r's will cancel, right? I have a 1 there, so on top. So I have a of t is equal to a times 1 plus 1 over m to the mrt. Then we're going to use something you may have forgotten. If you have a power So we're going to use this fact right here. If you have a power raised to a power, then this is the same as a, and what do you do with these two exponents? You multiply them together, right? So I could go backwards. If I start with a to the b times c, that's the same as a to the b, all raised to the c. So I'm going to write this, my previous function, in a slightly different way. I'm going to write it as 1 plus 1 over m to the m, and then I'm going to raise that to the RT. Okay, so I'm just using that rule. Right, it's called the power rule of exponents. I'm using that backwards. All right, now why did I do that? Because look at the term that's in the square brackets now. That should be really familiar. What happens, so as, if we take the limit as m goes to infinity, and remember, really we're basing it on the number of compounding periods goes to infinity, k goes to infinity, but we just said, using our substitution up here, if k goes to infinity, m goes to infinity, right? So if we increase the number of compounding periods, we're also really increasing m. But this term, what is this going to go to? This is going to go to e, right? That's the definition of e. So 1 plus 1 over m raised to the m, as m gets larger and larger and larger, it goes to infinity, that goes to e. So another way of writing this is I can say a of t is equal to a e to the RT. So, and sometimes R in this case is called the continuous growth or decay rate. All right, so here, let me wrap this up. So first of all, this would be the formula for if the interest is compounded continuously, right? That's what we derived there. And the R there, since we started off with our annual percentage rate, the R would be just the annual percentage rate in this particular application. So let me do this in general. So in general, the continuous growth function is given as f of x is equal to, so I'm doing it in terms of x now instead of t for time, so this is more general case, is a e to the rx, where a is a starting amount, just like before, and then sometimes people call R the continuous growth rate, or you could even, if it's negative, it'll be decay rate. So R is the continuous growth or decay rate. All right, so here's a question. Okay, so here's the question. We're told that radon 222, some element, right, decays at a continuous rate of 17.3% per day. How much will 100 milligrams of radon 222 decay to in 3 days? Okay, so our general equation is going to be, first of all, we know it's undergoing exponential decay, right? So we have our general function for exponential growth or decay is f of x is equal to a e to the r x. Why do I use that formula? Because it's continuous, right? It says a continuous rate of 17.3%. If I want, because we're talking about 3 days time, I could also write this, right? We call it x in general, but I could also use t in this case, right? Where t is going to be the time in days. So t is equal, let's say, time in days. All right, just by looking at that question, what are the other variables going to be? Well, a, right, little a, remember, is the starting value. So what is that going to be in this case? Well, it must be 100 milligrams, right? That's where we started with. R, well, the rate is 17.3%, but it's a decay rate, right? It's decaying. So this is going to be negative 0.173. I want to write it as a decimal, so I have to move that decimal point 2 places to the left. Right? If it's growth, R would be positive, decay, R is negative. And then t in this case is going to be equal to 3 days. All right, so now all we have to do is really plug in, right? So we have f of 3 is equal to 100, e to the negative 0.173 times 3. So this definitely you have to do in your calculator, right? Be careful when you do this in your calculator. Most of you should have a key that will allow you to do exponential. It'll either allow you to enter in the e itself, or it'll be like a key that says e to the x, and you can put in the exponent, right? So you need to find that in your calculator. And make sure, like, try this out, make sure that you're getting this correct answer. In this case, it should be 59.512 milligrams. So that's how much will remain after 3 days. Right? That's the amount you're going to have after 3 days. So we started at 100, it's decaying. At 3 days, you're going to have 59.512 milligrams. All right, great. So that was it for section 4.1. And then next, I'll start talking about, and we'll start looking at the graphs of exponential functions. So we'll get into 4.2. Let's see what these functions actually look like if we graph them. Great, thanks.